All right, let's get started on this week's topic. So what we're going to be doing are these non-parametric methods. So we'll go through the list, the one sample signed to the Kruskal-Wallis test. And as I mentioned in today's email reminder, is that we aren't doing the runs test. And that's because, well, mainly because StatCrunch doesn't have the runs test on it. But it's no big loss. It's an odd duck of a test anyways. In case you're curious, let's suppose you've just got like two categories of things and they're lined up and you want to know if they're in a random pattern or not. So it's kind of limited. It's just a situation where things are lined up and it's just two categories. Like let's suppose the two categories of people are freshman and sophomore and you wonder if they're just lined up in a random pattern or not. And well, you know, that's probably not going to come up very often. You need that. And it doesn't have a counterpart to it. You know, these non-parametric methods have a counter-parametric method, a first choice method, and this is the second choice. Well, this doesn't have that. So it's an odd duck. So really the ones we're covering are the important ones. Now, here's the big goal, what you want to be getting out of this week. Built into this is a review of some of the earlier techniques you learned. And these were early techniques that you probably only used your calculator on, and you may not have learned how to use StatCrunch with them. So this will get you weaned away from that calculator. You don't want to enter data in by hand. You want to copy and paste it in. Well, that's what you need StatCrunch for, so this will allow you to review that. Now, as you're doing these, this is the way you do it, how I'll be demonstrating it. I'll first check to see if the conditions are met for my first choice method. If they are, then I will use that first choice method. And I will only use these non-parametric methods if I have to, all right? Because that's the way we're going to use it in real life. So these are the second choice methods when you don't get to use the first choices. Now they're not that bad. It's just that they're just not as powerful and as efficient as the first choice methods. So we only use these when we have to. All right, so I'll begin with the sign test. Here, let's get this stuff out of the way. And what I'm going to do is what I'd recommend that you do, and that is we will have the instructions on one side. Let's see here. Let's get to the one sample sign test. So I'm going to have that over on this side. So that way, you know, you've got your screenshot instructions that you need. And so what I'm going to do on these is I'm just going to do the first homework problem in each of these sets. So that way you'll have a reference that'll get you started, and you'll at least be able to do the first one in the homework, as you know, I'll be demonstrating that. So that's why for this first one, this is the homework. And let's go over and fire up StatCrunch. So what I'll do there is I'm over here in my stat lab and just click over on StatCrunch. And we will go over to the StatCrunch website. And here's what I'm going to be doing. I'm going to paste the data into a form. So I'm going to click on that. Now, what I'm going to copy, well, I'm going to go over to the Word document. The nice thing about Word documents, it's actually, you know, pretty easy to copy the data from. So if I hover my cursor over there, see how it turns into that pointing down arrow? If I get it just right, then I click, it highlights the whole column. And then I'll just do Command-C because I'm on a Mac, and if you're on Windows, it's Control-C. We'll do that, and then you just go over here, click inside this box, and on the Mac, it's Command-V. On the Windows, it's Control-V. And of course, you know, you unclick, use first line as variable names, delimiter, make it tab. So that's all you need to do. And if we scroll down, click on load data, it should work out all right. Let's see if it does. It did. Look, it got it all loaded in nice and tidy. So keep that in mind. Whenever you have data in a table in a Word document, it's pretty easy just to copy your data from there. So that's what you're getting practice with here. All right, so we've got this. Now let's go. I'm done with this one, so let's get rid of that. So the idea is have your StatCrunch over here and then have your screenshot instructions over here. So first thing I'm going to do is I'm going to check that these conditions are met. Okay. Oh, and also we should make a note. And I just closed that Word document. I better get it back up so we can see what it was asking for. So let's see now. I had that all over here. I need to keep this handy anyways because I have to open each one of these up. So we're going to test a claim that the average is less than 15. And we're being vague by average because average could be, well, our first choice would be the mean, but our second choice is the median. Because, you know, average is a very vague term. Sure, we mostly think of the mean, but it's still a vague term, you know. So that's what we're going to see, what we're going to use for the measure of the center or the average. Okay, so we've got that. And we're going to check our conditions for the first choice, and that's what these screenshot instructions are doing. So what we're doing is we're checking the first choice. Now, you're probably just used to doing this on your calculator with t-test. Well, it's high time you learn how to do it with the highfalutin StatCrunch. And so what you do is you click, and once again, you're just referring to these screenshot instructions. Stat, and you go to t-stats, and it's one sample, and we've got data. And then, of course, you'll just go to scroll down here and you say, now what do I do? Well, click on that column that has your data. And then, now we're doing a hypothesis test. Once again, if we get our first choice, it'll already be all filled out for us. And what we're testing is the hypothesized value is 15, and the problem is interested in whether it was less than. So you just read the problem carefully so you know how to set that. And then you'll say, then what do I do? Well, just look over here. I got that. Oh, they want me to do these three choices. So let's do that. So that's going, and I'll have to scroll down here so I can see all of them. And we want this box plot. And what I'm going to do is I'm going to hold the shift key and click on this one. See, this normality test, this is a lot more helpful in determining if our sample is skewed than just using the QQ plot. So this is very helpful. We'll still look at the QQ plot, but this normality test is nice because it gives us a p-value. Box plots are pretty clear in letting you know if outliers or not. And this normality test will make it really clear whether your sample is skewed. Because you notice that we had a sample size less than 30. So the only way this will work is if our population is normal. Well, how are we going to check that? Well, if our sample has no skew and no outliers, it's reasonable to believe it came from a normal population. So that's why we're doing this. And as you'll say, is there anything else? No, instructions say you can just click on compute now. So that's what we'll do. Now let's size this up so you can see everything on here. Now, of course, we're not going to use this p-value and everything. This is just if we get our first choices. Now, down here, this is that normality test. Now, what you got to remember, and look over here in these screenshot instructions, what it is, the null says the population is normal. There's nothing unusual going around here. Think of it asking is how much skew is there, and the null says there's no skew, none, null. And the alternative says, oh, yes, there is. So a big p-value means you have no reason to doubt the null. Oh, okay, so it doesn't look like we've got a skew in our sample. So that's good, but we still need to check that box plot. So no skew, but let's go look at the box plot. Hey, there's no outliers. We got no skew, no outliers. It actually is okay for us to believe that this came from a normal population. We actually get to use our first choice on this. So on this homework problem, because the conditions are met, and be sure and show your work, show a picture of this box plot and a picture of this, show the p-value that telling you that, hey, this sample is not skewed and we have no outliers. We get our first choice. Hey, lucky for you, it's all right here. There's your p-value and there's your hypotheses that you're going to do. Well, look at that size of that p-value. That's big. Well, that's very big, so you're going to fail to reject the null. You got no reason to doubt the population mean. That's right, we're using the mean because we get our first choice, is no different from 15. Okay. There is not sufficient evidence to support the alternative hypothesis that the population mean is less than 15, or the average in this case. Now, just for practice, but that's what you would do. You just do it with your first choice, but I want to demonstrate how to do the second choice method without doing another one of your homework problems. That's the main thing. But let's suppose, like in some of the others, that, hey, things didn't pan out. Perhaps this p-value is less than 5%. Ooh, your sample is skewed. Or your box plot had an outlier. Oh, well, then you're going to have to go to your second choice. And how do you do it? Well, just follow these instructions over here. Let's get rid of that. And you're going to click on Stat. And it makes sense. We go to our non-parametrics. And this one is called the sign test. And then you'll say, now what do I do? Well, you just go to your screenshot instructions, click on the column that has your data, and you go down here. Now what we're doing is we're going to do a hypothesis test for the population median. So that's what we're going to do here. Now the hypothesized value, as you recall, it was 15. And we want to know if it is less than that. So our first choice is doing this for the population mean, but your second choice is doing it for the population median. And then you'll say, is there anything else? And no, that's it. That's pretty simple. Just clicking on your data and setting up your hypotheses, and then click on compute. And there's your hypotheses. So that's your population median. Your p-value is 50%. Well, that's pretty darn big. So you fail to reject the null. So you got no reason to doubt the null. There is not sufficient evidence to support this alternative hypothesis that the population median is less than 15. Now, even if it doesn't ask for it, it's real easy to follow it up with a confidence interval. The screenshots even make it even easier because they tell you all you got to do is click on this option buttons and edit this. And what are you going to edit? Well, instead of doing hypothesis test, click on confidence interval and then click on compute. Now, as a general rule, if it was a one-sided test, and I had 5% on one side, I usually change this to 90, just to make sure there's no contradictions. But then click on compute. Now, let's see, these look a little different. Now, we asked it to do a 90% confidence interval, and it's between 9 and 21. So you think, oh, I'm going to say I'm 90% confident in that, but here's a weird thing about non-parametrics. They have this achieved confidence. You say, well, we know you asked for 90, but what we actually have is about a 96.5 confidence level. I say, well, okay, so I'm 96.5% confident that my population median is between 9 and 21. And you note that your hypothesized 15 is in that interval. That's why we didn't reject it. Okay, so notice how we're getting practice with using StatCrunch for the statistical methods that you probably have only used your calculator for. And we're reviewing how to check the conditions for those. And either they're met or they're not met. If they're met, we'll do that first choice method. If they're not met, we'll do the second choice method. And that's all there is to it. Okay. So let's go ahead and try another statistical method. So we'll go ahead and we got that one down. And what we'll do next is the Wilcox and matched pairs. So the idea is instead of one sample, you have two samples, and those two samples are matched and paired up. Oh, and also it's quantitative numerical data. So if you got two samples of quantitative data, next thing you want to know if they're matched or paired up in some way. This says, but we use a 90% confidence interval because we're assuming it's a two-tailed test, so we need, this is the thing. Here, let me make a little sketch here. Because it is a little subtle what I said there. All right, so here we are. Now, if we had a one-sided test, but if you have a two-tailed test, you know, that's where you have the not equals in your alternative hypothesis. So let's suppose the alternative had been the median, population median, is not equal to 15. And of course, the null is that it's equal to 15. Well, notice that when that happens, your significance level, whatever, usually 5%, you have 2.5% over here, and you have 2.5% over here. So essentially, it's broken up in two. And so what do you have in the center? 95%. So once again, this is with a significance level of 5%. So now, when I have a two-tailed test, I just do the complement of this. So if this were 5%, I do 95%. But it does, because it just lines up so perfectly, because this 5% is perfectly split in two, and you got the 95% perfectly in the middle. But what happens when it's lopsided? It's all lumped up in one tail. So let's suppose, you know, that we're doing the less than. So instead of 2.5, I got the entire 5% all lumped up over here. Now, and I'm going to switch colors here. And if I do a middle 95%, things just don't match up as perfectly anymore, do they? Do you see this region where I got two colors shaded in? That's an area of contradiction. If I used a 95% confidence level when I had a 5% significance level, I want to avoid having this. So how's a nice way to avoid that? Well, that's why I did what I did. If I've got a one-tailed test with 5% over here, I'll say, well, why don't I also put it over on the other side? And then I ask, well, what's left over in the center? 90%. In other words, this way I don't have any contradictory areas. That way I don't have to worry about my confidence interval contradicting my results of my hypothesis test. So that's what that is. But that's usually, you know, well, I give you the confidence level, but of course you wouldn't have that if on your own you're following it up with a confidence interval, so therefore it's helpful for you to know this. Okay, so here, let me go ahead and erase that. All right, now let's see here. So we're going to be working with these matched pairs. Now your first choice, of course, is looking at the population mean of all the differences between all the possible matched pairs in the whole wide world. So remember, when you're working with two samples, you're talking about things you could never really do. Yeah, let's suppose we're using twins and we're comparing the measurements we're getting from twins. One's getting one treatment, one's getting the other treatment. Well, you have to take all the twins in the world and do this test on them, and you'd like to know what the population mean is for all those differences. Well, you can't do it, but that's why we got inferential statistics, so we can get an estimate of what that would be if we could have done that. Now, that's our first choice. Now, what are the conditions? Of course, that's matched pairs and all, of course, but you want to look at the population of all the differences either needs to be normally distributed or your number of matched pairs is at least 30. So if those conditions are met, you'll use your first choice method. If they're not met, well, that's where your Wilcox matched pairs test comes in. Now, I probably need to edit my notes because I'm using a capital M. It'd be much better if you wrote out median. The reason is a lot of people, their capital M's, you can't tell them apart from their mu's. And then nobody can tell whether you're talking about this or this because your M's and your mu's look identical. So that's why it's best to write out median so everybody knows what you're doing. Now, of course, you can see the relaxed conditions. Not as relaxed as the last one. The last one, all you needed was a random sample. This one has an extra little condition where the distribution of the differences, or just talk about the differences, it's symmetric. You know, it could be uniform, maybe even bimodal, just so it's not skewed. So there's still a catch to this one, but it's not as big a catch as it was for the first choice methods. Now, just so you know, I don't really get too much into checking that. What we kind of just do is if can't do this, well, we'll do this one because that's all that we got left. All right, but you should be aware of that. So what we're going to do is I'm going to shrink this down so I have enough room for the stat crunch. So we just need this for handy reference, reminding us of the steps that we're going to do. Of course, what we're going to do is first do the first choice methods. So let's go over here. I'm going to go ahead and close that. We're going to go over here. We're going to paste the data into the form. Then, of course, I'm going to call up the homework, the Word document that has your homework on there. And so we're going to do the Wilcox and matched pairs. Let's get that out of the way. And so we better shrink this down a smidgen bit. So what are we doing here? Well, we're going to send these rats out into outer space. But at liftoff minus 3 days, so before we send them out in outer space, we're going to take these measurements. And then after they get back from their trip into outer space, we're going to get another measurement. So classic before and after measurements for each rat. So those are obviously matched pairs because each pair are matched up to its own dirty rat that got sent out into space. Okay. And what we want to know is if these measurements are less than these. So in fact, I'll go ahead and copy this in, but then we'll come back and we'll have to keep straight, you know, what's being subtracted from what. So you notice how I just clicked and dragged after it turned in that down arrow. And then I can do my, Command C or Control C, depending on what you're using. And then we'll just go over here, click inside here and paste it, Command V or Control V. That's selected and delimiter is tabbed. All you got to do is scroll down and click on Load Data. And it is in. Okay. Now, in fact, maybe I'm going to scribble this up here, something that we need to keep track of. And I'm going to scoot this over here so we can see this. Okay, so it's not scoot. There we go. Down there. Okay, so we're going to jot this down because you don't want to do this in your head. It's too easy to make a mistake. All right, so here we go. Maybe I'll do it right up here. This will be out of the way. So our differences, we'll call it diff. I'll just put in my first one, which is the HL3, and I will subtract my second one, which is the HRO. I'm not putting the dashes because that'll look confusing with the subtract. And they want to know that HRO, or the HL3 is less. So this one is smaller. So imagine taking a small number and subtracting a big number from it. What do you get when you do that? Small number minus a big number gives you a negative number. So that means that these differences would be overwhelmingly negative, more often negative than positive numbers if this were to happen. And we know negative numbers are less than 0. So that means our mean or median of differences will be less than 0. So we need to know that when we set up our hypotheses. Okay, so we got that figured out. I think we can get that out of our way. So let's go ahead and let's just follow these instructions over here. So we're going to do stat, t-stats, and we're going to pair because we got matched pairs. Let me move this down so it's not, I'm out of that writing. There we go. And it says, over here, so first, once again, I usually just put my first sample in here, which is the HL3, and my second sample over here. And remember what it does your sample 1 minus your sample 2. That's what I had figured up here. Over here, instructions say, click on the differences there. It's nice to have those stored in a column. Then we got to go and set up our hypotheses. Okay. And once again, our population mean of differences, that's what this is. The null says it's equal to 0. We want to know if it is less than 0. So how did I figure that out? That's what I did up here to make sure I use the correct inequality. Keeping track what was smaller, what was bigger, what I subtracted from what, and what that would result in. Then it says go down here, and we want to select these choices. I'll click here and I'll hold down the shift key so all 3 of these are selected. Once again, we'll have that normality test. That'll tell us very clearly if our sample is skewed or not, just like we did on the last one. And of course, a box plot will let us know if there's outliers. And it is doing this for the differences. So it's smart. It knows to do that. Unlike when you did this on your calculator, you had to remember to do it with list 3 if you had your data in there. All right. And also, you notice that our number of matched pairs is less than 30. And so then what we're doing this is to see if it's reasonable to believe that the population of differences is normal. Now it tells us over here, we got everything set. Just click on compute. So with confidence, you click on compute. You don't have to worry about, did I forget anything? That's why we got screenshot instructions. All right, so let's go down here. Now, don't really look at this yet because you only get to use this if your first choice method is allowed if the conditions are met. Well, we got a big p-value, so remember our null and alternative. The null says there's no skew, and the alternative says, oh, yes, there is. Well, this is a big p-value, so we got no reason to doubt the null, so it's reasonable to believe there's no skew in our sample. So that's good. I get when I say sample, I should be saying our differences between our matched pairs that we have. there is no skew. Now we still got to check the box plot. Oh no, look, we got an outlier. Well, no first choice for you. So, in your work, have a copy of this and the results and say, okay, even though there was not a skew in our sample, there was an outlier. So the conditions are not met for our first choice. Let me just click on this because we don't get to use it. All right. Okay, so we'll go over here and see now what was that second choice? Oh, once again, this is explaining all what we just did. This tells us right here. So we have to do the second choice on this one. So we'll go over to stat and go down to nonparametrics, and it's the Wilcoxon signed ranks. Select that. Then, and of course, this is reminding you, this is what you at least write median, but it's even better if you're making super clear, you're talking about the population median of the differences. And of course, we'll be doing less than 0. Now, you actually have 2 different ways you can do this. Now, this is showing clicking on paired and putting, this in my first sample and this one in the second sample. Or, what you could do, I could click on one sample and do the differences. Because see, when I ran that first choice method, it put the differences in this third column. You don't believe me, huh? Okay, well, let me show you. See, it put the differences there. So you'll get the same result, same p-value. Then I really don't think there's a benefit of one over the other. So I'll tell you what. The screenshot instructions show it being done this way, so why don't I show it being done the other way? So I'll click on differences there. Now you'll still need to set this up. So remember, it's equal to 0, and up. Remember, this is going to be less than 0. If these measurements are going to be smaller than this one, then the population median of the differences should be negative. All right, so we got that. Now let's see, is there anything else? No, that's it. So I'll click on compute, and there's your p-value. Well, that p-value is less than 5%, so we can reject the null and accept the alternative. There is sufficient evidence at the 5% significance level to support the claim. The population median of all the differences is less than 0. Now, of course, you're wondering, well, how much of a difference is there? Well, the screenshot instructions will show you it's real simple here to follow up with a confidence interval to see how big that difference is. So you just click on options, click on edit, and let's just change from a hypothesis test to a confidence interval. Now, because it was one-sided, I'm going to do my little trick again of making this 90%. Same reason as before. Click on compute. And so ask for 90, but you know how weird nonparametrics they are. So, well, actually it's 90.77. Oh, well, whoop-de-doo. So you can say 90.77% confident. The population median of the differences between all the match pairs. So imagine sending all the rats into outer space, and you got these before and after measurements. And what would be the mean of all the differences between the matched pairs? Well, it'd be somewhere between a negative 1.55 and a negative 0.25. So this is telling you how much smaller or how much bigger the measurements are upon their return. It might only be 0.25 of these units larger, or it might be as much as 1.55 of these units larger. So, of course, we'll have to call in an expert with the data to tell us if it was just this much bigger, would that be of practical significance or not? And if they said no, I said, well, what if it was this much? And they say, yeah, that would be significant. We go, oh, great. You know what this means? We need a larger sample size in order to crunch in our confidence interval. Well, if you increase the sample size and you send more than 30 rats up there, are you going to be using this statistical method? No, because the conditions will be met for your first choice. Okay, so those are the concepts I want you to keep running through your head on every homework exercise you do. You're starting to really appreciate how important it is you know how to check the conditions for the first choice methods so that you know whether you need to use the second choice or not. And of course, anytime you look at a confidence interval and realize it's not narrowed down enough, and you're thinking you'd have to increase the sample size anyways, a big benefit is, hey, then I get to go back and use my first choice method. Because increasing the sample size to the point that you get your first choice method. So remember, that's what increasing the sample size can do for you. It can get you your first choice method if it's increased enough. All right, so let's go ahead, shut that one down. Now we'll close this one. And now, so let's imagine we have two samples of quantitative numerical data, but they are not matched or paired up. Okay? So that's where we get over to the MannWhitney test. Once again, let me shrink this down a little bit. Move it over here. And of course, there's our first choice method. So notice how the hypotheses look different when they're independent like this versus when they were matched pairs that we were just working on. And here's the conditions. Of course, you got two random samples. Samples are independent. Now that has to hold for the second choice method, but things are relaxed on the third one. Here, either both populations are normally distributed, or you have sample sizes of at least 30. Over here, we're saying, well, the distributions of the two populations are the same, whatever that is. You know, maybe they're both right skewed. Yeah, that'd be okay as long as they're both right skewed or they're both left skewed. Okay. And so the only thing that might be different would be the median, okay, even though they still have the same shape. So, you know, this is more relaxed because it could be that you're dealing with skewed distributions, you know, right skewed like you have with real estate prices or salaries, things like that. So this could come in and save the day. And the whole idea is that you're using population medians instead of population means. All right, so let's call up a homework. We'll do the first one from the homework you had. No. What did I do? Oh, maybe I closed that. Well, why would I do a thing like that? Yeah, I really did. So let me go ahead and we're going to do the MannWhitney test. So this time I'm just going to shrink it down instead of closing it. Oh, let me get rid of my drawing here. We don't need that anymore. There, that's better. So let's go over here. Scooch you on over here. Let's get this pasted in. But let's see, what are we doing? We are comparing the weights of NFL defensive tacklers with offensive tackles. Okay. And I guess we're comparing their weights. We're wondering if the weights of the offensives is higher, larger than that for the defensive. All right, we just got a random sample from this population, a random sample from this one. So let's go over here. Let's close this one. And what we're going to do, as before, we're going to paste data into the form. And let's just go over here, get my cursor to look like a down arrow, click and drag, then copy that, click over here and paste it. Those are selected, that's tab delimited, then just click on load data. There it is, all loaded in. Now, so what we should probably do, we're going to make a note up here. We want to know, because we're going to put this away and we'll need to remember a few things. So we'll write down what we need to remember. So we've got the offensive. We want to know if this is larger. So this is larger or heavier. And defenses, this will be lighter. We'll say the numbers are smaller. Just so we can keep track of what they're asking. All right. So that should be enough to jog our memory when the time comes up. And we can go ahead. I'll shrink it down just in case I have to call it back up again. All right. So let's go on over here. And this will step us through what you're doing. So first thing is our first choice method. So let's go over here and click on Stat, T-Stats, to sample, not paired this time, but to sample with data. Okay. And then just put the first sample in here. Let me do this. So you can see this. There we go. So we're going to set sample 1. I'll do the offensive. Just put my first sample there. And down here, second sample over here, defensive. Okay. Now, this is interesting because my lecture note says, now be sure to uncheck pool variances, but it's already unchecked. So that's why I was glad they made a note here. Oh, this was recently changed to off, which is good. That is an improvement because we never want to pool variances because that's claiming that we know for sure that the population variances are the same. Well, we don't. So let's just keep that unchecked, especially if we have to go to second choice methods. Now, so this is where it's helpful. Now, of course, the null is always that if you subtract these and they're the same, it'll be equal to 0. Now, population mean, that's our offensive, so that would be a big number. So if you have a big number and subtract a smaller number, it's positive, right? Yeah. So that's how I know this is greater than, because these are the large numbers minus. That gives you positive. So once you got this, so that's why I wrote that down up there, so I knew which inequality to put in here. Now, let's go down here. And so it does these 3 choices. So let's be sure and do that. And I'll have to scroll down a little bit here. So we want the box plot. And I'm going to hold down the command key on the Mac, control key on Windows, and click QQ plot. We don't really need the QQ plot. All we really need is Shapiro-Wilk normality test to tell us for sure whether we have skew or not, and the box plot to tell us for sure whether or not we have outliers. Then click on compute. All right. So now it's showing all these results that we could use if we get to use our first choice. But before we do that, let's see if we get our first choice. So here's the normality test. And so what it's doing, it's looking at both of these. Because remember, we're looking at 2 populations now. It isn't like with matched pairs where it was simplified down to just the differences. Well, for the population of the defense, it's simple. It was telling us, hey, there's no skew, but for the other population, there is a skew. Well, they both have to be normal. So this right here kills it for us. No first choice for us. Well, might as well also let's check the box plot. Oh, offensive. Not only does it have a skew, it has an outlier. So because of this population, we can't use our first choice. You know, not with small samples like this. Now, if we had gotten, if both samples were at least 30, we could have used our first choice, but not with these small samples. So you see all this? You don't get to use that. So let's just put it away. But before you do, of course, you probably want to paste this in your work documenting why, and this in your work, why you are using your second choice. And don't get your first choice. So let's get rid of that. And then you're going down here and saying, now what is that non-parametric methods? Because you see, you don't get your first choice and you're going, oh man, I'm at wit's end. What am I going to do? Well, I'm going to use the MannWhitney test. If you get to it, you press the stat, non-parametrics, and there's your MannWhitney test. And of course, instructions are going to tell you what to do, but this is pretty simple. You know, you just put your first sample in here. That's our offensive. Put your second sample over here, defensive. And as we already figured out, this will be larger than 0 because the population median 1 is from these larger, more heavy offensive tacklers minus the smaller, the lighter ones. So that's why that's positive. So you got that set and that set, and that's it. So there's less to do. Okay, so you click on compute because before we also had those graphs to do, but we were doing the graphs to see if we got our first choice or not. Well, we already know we're doing second choices, so we don't need any more graphs. Click on compute, and there's your p-value. Hey, that p-value is less than 5%, so we're going to reject the null and accept the alternative here and say yes, indeed. The population median for the offensive tacklers is heavier, larger than it is for the population median for the defensive tacklers. So now, this population median is larger. You say, but how much larger? Well, that'll be easy to do if you use these screenshot instructions. Click on Options, select Edit, and click on confidence interval. And since it was a one-sided test, I'm going to make this 90 instead of 95 and click on Compute. So it's a 90% we asked for, but it's actually going to give us a 91.7%. Okay, well, good. But so we're 91.7% confident that the difference between our population medians is between 5 and 40. So that means this population median for offensive might just be 5 pounds heavier, or it could be as much as 40 pounds. Now, that might not sound very narrowed down to you. You might say, well, gee, I got to get it more narrowed down than that. Well, get yourself larger sample size, and while you're at it, get sample sizes that are at least 30, and then use your first choice method, right? So please run those concepts through your head on every one. First choice, second choice methods, how you could get your first choice if you got your sample sizes big. All right, so that takes care of that one. And let's get rid of our annotation there. And so that's for the MannWhitney test. Now, this next one, this is what our second choice when you're doing regression and the conditions aren't met. So you remember the conditions. In fact, those are things you were just having to state and do on your exam 2, which you finally got back today, this afternoon. You should have in your email. If you didn't, please let me know. Now, so remember the conditions. The residuals are normally distributed, not the data. The residuals need to be normally distributed. And you look at the residual, and to do that, we would look at the probability plot and the box plot. And then we make the residual plot, make sure there's constant error variance with no discernible pattern. And hopefully no influential outliers. Okay, and then of course we went ahead and did what we did, just like you did on exam 2. But what if those conditions aren't met? Well, we have a second choice methods, and it's got very relaxed conditions. this is great because your random sets are of n-ordered pairs. Well, yeah, we definitely would always have that. Okay? And each pair of observations is 2 measurements taken on the same individual. Well, yeah, we would have that. So this is great. You know, we'll definitely be able to meet this. This is way more relaxed than all these conditions over here. Okay. Now, what's a little different about this one is there's 2 steps to it. Each one is a very simple step, but that's different. That it's a 2-step process. All right, so let's do this. Now, this one doesn't. Lecture notes don't really remind you of checking the conditions, but you just did that. Okay, so that's why I didn't bother to go through that. But I'm going to do it now, though. So what I'm going to do, we got to get the data in there, don't we? So let's go take a look at our ones for the Spearman rank correlation coefficient. Let's see if there's a correlation between a student's midterm score and their final score. All right, let's do that. So I'll go ahead and click and drag, and I'm going to copy that. And we'll go over here, paste data into the form, click here, paste it, everything's all set, click on load data. All right, it's in there. All righty here, so what we're gonna do, we'll do stat, regression, simple linear. And let me shrink this down so we can look at this up here. So it's nice, they make it very clear. We're trying to predict the final, which makes sense because you have a midterm before a final. So it makes sense that this is what you're using to predict that. But still, it's nice when they make it super clear with the X and the Y. So there's no way to confuse that. Okay. And with regression, we always have it where this is 0 or not 0. It's really the slope that comes out. Really don't care about the intercept. It's the slope we want to know. And of course, if the slope equals 0, that's just another way of saying that there's no correlation. It's just a hodgepodge of data. It's just a hodgepodge. You might as well just use a horizontal line, and horizontal lines have a slope of 0. Now, what we can do over here, scroll on down here, we could look at this QQ plot residuals and also at the residuals. So I'll have to hold down my command or the control key on Windows so that I'll be able to look at that. And also I better under save click on residuals. So that way I'll be able to make a box plot of the residuals. Because I'll have the QQ or the probability plot, but I also should make a box plot of the residuals. So we got that. There's nothing else in here for you. All right, and then we'll go ahead and click on compute. Now, this is what you'd get to use if you get your first choice. Now, as we look at this, let me click over here. Now, that's my QQ plot. You're saying, maybe that's all right. Okay. Now that's the residuals. Now that's not looking too good, does that? Doesn't look quite right. Okay. Remember, you want constant error variance. Here's the line. Let me put that in there so you can see it. And it doesn't look too good. Because right on the right end seems to taper, and you looks like a value way up there. And then another one way off to the side. You're probably not liking the looks of this. But let's go ahead and make the box plot. So I'm going to go over to Graph. And we'll go do the box plot. And see, it created the residuals for us when we ran that test. So that way I can do this. Oh, this is another change they made. by default, they have this turned on. I love that. It used to really annoy me that they didn't have this turned on by default. So I'm very tickled they made that change. I'll probably just draw them horizontally. And if you want, we could also have them over the same x-axis. Oh, but we only have one, so there's no need in doing that. So let's click on compute. Uh-oh, you got an outlier. So you definitely don't get your first choice because my residuals has an outlier, so it's not reasonable to believe that my population of residuals is normal. All right, so no first choice for you. We're going to have to use this second choice, the Spearman rank correlation coefficient. So let's go ahead. Now, of course, you could be copying and pasting those into your homework, documenting all of that. And what we're going to do, let's scoot this on over. And let's see what they say to do. I don't know why that. It's okay. Oh, yeah, good. I can uncheck it. It looked a little weird having those in there. All right, so what we got to do before we do the Spearman rank correlation. Now, here's our hypotheses. X and Y are not correlated. There's no null, no correlation. X and Y are. Now, first thing, it's a two-step. First thing, we're going to actually rank the data. It's really easy to do. The screenshot instructions show you. Just click on data and click on rank. And down here, all you do is select both X and Y. So I'll click on that, hold down Shift, and click on this, and click Compute. So that's super easy. Now, let's look at what they did. What did it actually do? Well, it's ranking all your data values. The smallest is this one. What's the next smallest? 2. Oh, 72 is the next smallest. Next smallest is 80 because that's 3. So it's just putting the ranks of the data values. That's how this method works. So you do that first, then you can run the Spearman test, as this explains. So you just do stat, nonparametrics, and the Spearman correlation. And then the instructions tell you. Now what you select is not X and Y, but the ranks. This one and that one. So that's kind of funny. The two-step process. Make sure you select these and not anything else. And then we will always do a two-sided p-value for these. And that's it. You just click on compute. So that's pretty straightforward. Just select the two ranks, select the two-sided p-value, click on compute. Now, this is kind of weird, but this is why you have the screenshot instructions. Inside the parentheses is your p-value. So it looks kind of funny. Now, it doesn't come out and say p-value like we're used to. But that's why we got screenshot instructions. So you say, oh, okay, my p-value is 0.5, about 0.51. That's a big p-value. And remember, here's your hypotheses. So you fail to reject the null. So you got, there is not sufficient evidence to support the alternative that they are correlated. So it doesn't look like they're correlated. There's just not enough evidence to support saying they are correlated, right? And so there you go. That's how that one's done. So you know, when you actually use these, it's pretty simple filling in the boxes. But you notice, well, as you're doing this, one, you are reviewing how to check conditions for linear regression. That's a good thing. And you're checking them. And then if the conditions aren't met, you know the second choice method. And you know these conditions will always be met. This is really relaxed. So you know that you always got something you can fall back on. Now, true, it's not as powerful and efficient, but it can get the job done. All right. So we got just one more method to do. And it's the second choice whenever you do a one-way ANOVA. So we'll review the 4 conditions that have to be met for one-way ANOVA, and if they're not all met, what we can do about it. So let's go ahead and get rid of this one. Shrink this down a smidgen bit. So remember, here's the 4 conditions. The 2 pretty straightforward, and of course, these are simple random samples, and they're independent random samples. Those are pretty straightforward, but you got to do some work to check 3 and 4. The populations are normally distributed, so you look at the probability or QQ plots and the box plots, and then check for if we have this equal population variances. And you check this by looking at the sample standard deviations, making sure the largest isn't more than twice as big as the smallest. But if these don't work out for you, you can do the Kruskal-Wallis test. Okay. Now, you would think that it would be using population medians instead of means, but that's not actually what it is. How you state it is the distributions of the populations are identical. Whatever those are, whatever that distribution is, whatever crazy thing it is, that they're identical. Well, the alternative says no, they're not identical. So watch that. It's easy to get this one wrong because of our previous ones. We just would always substitute mean with median, but yet this one isn't quite like that. Now, is it pretty relaxed in this condition? So let's check it out. Well, each sample is simple random sample. We always have to have that, so that's not demanding. Each sample is independent. Okay, that makes sense because those 2 are always ones to easily verify. 3, the data can be ranked. Well, that's easy. So we can easily meet these conditions. We don't have to worry about not being able to meet any of those conditions. So this is very, very relaxed conditions. So we're going to try this. And once again, I'll just do the first homework problem from that homework set. So let's call that up Kruskal-Wallis test. Close that. So we're checking radon levels of 4 public schools. So we're comparing these 4 populations with each other, and we took a random sample from each one. So we got 4 independent random samples. So that takes care of 2 of the 4 conditions. But let's go ahead and let's do our little click and drag. Copy that. And we'll go over here. Paste data into form, paste it in there, and scroll down, load data. All right, it's all in there. And of course, the null, as you know, is that their population means are all the same if we get our first choice. Alternatives, at least one is different. Okay. Now you notice here that I am kind of reminding you how to check the conditions, even though it should be real current in your memory. But let's go ahead and do that. So let's go and graph. And we'll start with the box plots. So we'll make box plots of all of these. And I'll just draw them horizontally, and I'll just go ahead and put them all over the same x-axis. Click on compute. Well, there's no outliers, so that's good. All right. And so, of course, you can copy and import that into your document. And we can also do the QQ plots. And so let's do QQ plot. And let's select all of them. So I'm holding the Shift key and then clicking on the last one. Let's get the correlation statistic in there too. It's a little more helpful. Click on compute. Let's look. All of these look pretty good. It doesn't seem to have any skew, so it seems like they're coming from normal populations. So now we need to check for equal population variances. So what I need to do is look at their sample standard deviations. So we do stat, summary stats, and columns. Let's select all of these. And all we need to look at is the standard deviation and compute. And look at this one. I don't even have to get out my calculator. I can see that's more than twice as big as this one right here. Well, the conditions aren't met. We don't have equal population variances. And you can't use the one-way ANOVA without that condition. So you're going to have to go to the Kruskal-Wallis test. So once again, you're reviewing how to check those conditions. Now, so we're going to go over here and just follow these instructions. And I think you'll find this to be a pretty simple one to use. So we'll just do stat, nonparametrics, Kruskal-Wallis. And as it says here, you're just going to select all of these like that. So and look at the instructions. Just select the columns, hold the data, and click on compute. That's it. You say, are you sure I don't have to do anything else? Nope. All you got to do, select them. I told you you're going to find it pretty easy to use. And here it clearly shows your p-value. Well, that's great. You can see your p-value. You know at least one is different. But you say, well, where's my Tukey test? Well, you're going to have to settle. Now you probably say, oh, darn it, I deleted my box plots. So you'd have to use that as a guide to identify now which ones are different. Well, of course, you probably noticed when we made that how different they were. But you make sure to use the same x-axis because that's what allows you to compare them with each other. So doesn't it look like this box plot is very different from these two? And it might overlap a little, but so it might be debatable. It looks like at least some difference, but there's a huge difference between these. And there's definitely a difference between these pairs here. So you can use the box plot as a guide letting you know which ones are different. But you say, but that's not as powerful and efficient as the Tukey test. Well, that's why we call this nonparametric methods. They're second choices, baby, not first choices. This is all you got. All right, so that's a rundown of all the nonparametric methods. The real value from doing this is it gets you to review all your first choice methods. Also, did you notice something that the first choice methods we looked at involved quantitative numerical data? How come we didn't do any with categorical data? Because with categorical data, you need such large sample sizes that if your sample size isn't even large enough to meet the conditions, your confidence intervals are going to be so wide, they're useless. Things just aren't narrowed down enough if your sample size isn't even big enough to meet the conditions. Usually, your sample size has to be way bigger than is required to meet the conditions just so you can get things narrowed down enough till you actually have the answer to your interesting questions about the world. So there's no point in having second choice methods for categorical data. All right? So in case you were noticing that. So if anyone's got any questions, feel free to ask away because we've got it all covered here. And also, you probably should notice that, boy, these methods sure seem a lot easier compared to those other methods we did, like two-way ANOVA. That was pretty involved. Okay. Really, that's the toughest one of all because you got more concepts to remember. And, sometimes multiple regression has some concepts in there you got to remember. But especially like Kruskal-Wallis, it felt like there's hardly anything to do to run it. You just selected the columns and clicked on compute and you had it. Okay. Oh, also, I guess I should say that you've got these medians, so you can sort of use these to compare, but the box plot was a nice visual way to get an idea of which ones were and were not different, just by seeing how the box plots overlap. The box parts of the box plots overlap. Okay, well, that's it for this session.